Today we're going to start talking about what a limit is. We're not actually going to do any limits today. We're just going to talk about the general idea. So in the most simple terms we can come up with, a limit just means what y value does our function approach as the x values get really close to, well, some a value. So here we've got some a value. As our x values are approaching that, both from the right hand and from the left hand side, we can see that our y values are approaching this point right here. We could call this point to point A, comma L if we wanted to. And we would say that the limit as x approaches A of this function, f of x, is equal to L. That's just this length here stretching from the x-axis up to our function. Okay. And the notation we'll use for this looks just like this. The limit as x approaches A of f of x. That's how we read that, and that's how we're going to get used to writing out our limits. Okay. So that's the whole idea. What value do we get really close to as x gets very close to whatever a value we're interested in? So we'll just kind of start moving forward here. This is going to be kind of quick today. First question we're going to ask ourselves here is, does it make a difference if the point at x equals a is not defined? Okay. And so the way I just sort of started this off here was to say that what a limit is the y value that we're getting close to as x gets close to a. Now, I never said what y value are we at when x gets to a. There's a very distinct difference there. Right? All we care about is what y value are we getting close to as x gets very close to a. So as x gets very close to a, but doesn't actually necessarily get to a, the y values from both sides are again getting very close to the value of L. Now, we've got the open circle there indicating that we've got a discontinuity in our function there, right? That there's not actually a point there at x equals a. But that doesn't matter for a limit. For this, we would still say that the limit as x approaches a of f of x is equal to L. Because as x gets very close to a, the function gets very close to L. That's all there is to it. So as we do this, we're going to try and ask ourselves two different questions. The first is, as f of x gets close to a, as x gets close to a, that should say as x gets close to a, not f of x. As x gets close to a, does the value of f of x get closer to some real number L? Right? So that's the first question we'll answer. Hopefully the answer will be yes. And then our second question that we'll ask is, can we make f of x get as close to L as we want by choosing x values that are closer and closer and closer to a? And if the answer to both of those is yes, then we would say the limit exists and that limit is equal to L. So if we think about that, we look back at, let's say, this one. The first question is there some y value that f of x gets closer to? The answer is, yeah, it gets close to L as x gets close to a. And we can get as close to L as we want. Let's say we wanted to get within 0.001 of L. We just have to pick an a value or an x value that's very, very close to a, so that the y values would be within 0.001 of L. The same is the case with this one, right? We can get as close to L as we want by picking values that are closer and closer and closer to a. If I wanted to be within 0.001 of L, then I just have to pick something really, really close to a. And if I wanted to get as close as, say, 0.00000000001 away from L, that's fine. I can do that. I just have to pick an x value that's even closer to a than the previous one I chose. And so those are our questions. Is there something we get close to, and can we get as close to that as we want by picking x values closer and closer to a? So we'll ask ourselves those two questions every time we think about a limit. And if they're both yes, then we know the limit exists at A, and it should be equal to that value out. Anytime we have a function that's continuous on its entire domain, the answer to both of those questions is going to be yes, for the entire domain of the function. Okay? And it's important also for us to remember that the limit is not necessarily going to be the actual value of the function at A. Sometimes it will be, and sometimes it will not be. Sometimes the function won't be defined at A. So when we have functions that have discontinuities at A, we're going to have to take some special care with those limits. And that's our really basic introduction to limits. Next time, we're going to talk about the formal delta epsilon definition of a limit. And then after that, we'll get into some nice, quick, and easy ways to evaluate limits. But that's going to be it for today.